Question 5 is the calculus question. I start you out by giving you a velocity function. Remember, I am restricting the domain. We're just not really going backwards in time. So we're just going t greater than or equals 0. And we want to find the position function given the initial value, x of 3 equals to 5. Remember, you're going to use this to find the integration constant. In a calculus class, you might call that a plus c. But in physics, we know what it is. It is the initial position, so I just went ahead and called it x naught. Remember, to find the position from velocity, we need to use the reverse power rule. We need to increase the power by 1 and divide by the new power, which I did here. Increase this t squared to t cubed and divide by 3. Increase t to t squared and divide by 2 to make it a negative 4. 12 becomes 12t plus x naught. And then I plugged in 5 for x, 3 for time, and found x naught to be negative 4. And so then this is, the full equation that describes the object's position as a function of time. Acceleration, well, that's easy. That's just the normal power rule. That's just the derivative of velocity. Remember, the definition of acceleration is the rate at which you change your velocity, so it makes sense that it's the derivative. So I just took the derivative of t squared to get 2t, the derivative of negative 8t, and get negative 8. All right, and then we have some of the classic pre-calc type questions. When is the object stopped? The object is stopped when the velocity is equal to 0. I set the velocity equal to 0. In this case, the numbers were easy enough to factor, and so I just factored it. I'm also going to use the same information for the next question. Find when the object is moving left. The object is moving left when the velocity of the object is negative. The velocity is negative. I did a sign chart. And again, you're looking here. The velocity is 0 at 2 and 6. 2 and 6. 0 is an endpoint, so I just threw that in there. Between 0 and 2, the velocity is positive. Between 2 and 6, the velocity is negative. So really, the object is moving left on the interval 2, 6. Find the speed of the object when it first gets to the origin, because it might end up at the origin more than one time. It is a cubic. So remember, the origin is simply when x equals 0. So I just took my position equation and set equal to 0 and solved. That's when I'm at the origin. And then I took that value and plugged it into the velocity equation, right, that was given to find the velocity at that moment and got the 9.1 meters per second. When is it speeding up? Again, I took the velocity equation and I looked at the absolute value of velocity, which is speed, and I looked at this. And then when you're looking at this, it's pretty easy to tell that the speed is going up when the graph's going up. So from 2 to 4, and then from 6 to infinity. On these intervals, the graph of speed is getting bigger. It's a little harder to look at the actual regular velocity curve, but looking at the speed curve, it's easy. Does the object ever get back to its starting position? Sure. Why don't we just, starting position is negative 4, and why don't we just graph and see if there's an intersection between those curves? So I just graphed negative 4, and I graphed the position. I'm like, oh yeah, look at that. When t equals 6, so after 6 seconds, I'm actually just back to where I started, and after that, I'm going right for the rest of the time. All right, rock question. Rock A and rock B. I chuck a rock up, I chuck a rock down, and I want to know all sorts of stuff. So the first one says find time, location, and velocity of the collision. So here's our standard free fall equation where we're under the influence of gravity and gravity only. If we want them to collide, we want their heights to be the same. So I just set the rock A function and the rock B function the same. Rock B is thrown up from the ground under gravity. Rock B is on a building, thrown down with gravity. And you notice algebraically, the two quadratic terms cancel, and you can easily solve for t. So you get a time of 2.67, and then you can plug that into either one of these equations to figure out the height is 18.5 meters. And again, you can plug them into both. You better get 18.5. That was the whole point of that question, that they are literally at that time, they are at that location. And if I wanted to find their velocities, again, I'm looking at the standard velocity equation in free fall. One was thrown up, gravity for a certain time, thrown down, gravity for a certain time, and I can get their two separate velocities. Do they collide before or after rock A has reached max height? Again, rock A is going to go up and then come down, and the question is, when does rock B hit it? And if you think about at the collision, the velocity of A is negative, right? We already decided that here. That must mean that rock A is already on its way down. So yeah, the collision is after after it's reached max height. And if you want to actually find max height, well, I just graphed the y. I just graphed this, right? Just graph the position function of y and then look. And so it's actually at a max height at 2.04 and 20.4, where the collision happened at like 2.67 seconds at a height of 18. So it's like right here at the collision. Which rock hits the ground first? How fast do they move when they hit the ground? Again, assuming they don't collide, right? Because otherwise they're not going to hit the ground. They're going to, like, I don't know, whatever, shatter each other. But as they pass, think about A was already moving down at 6.17. B was moving down at 36.1. So clearly, rock B is going to hit the ground first. And then you can just graph them. Rock B hits the ground at 3.15. And you can plug that in to the velocity equation of B, which is right here. And you can figure out that's how fast it's moving. Now, rock A, I actually didn't do anything for. I just used symmetry. We know that rock A was thrown up at 20. Gravity's going to pull it up, slowing it down, and then gravity is going to speed it up the same amount of time. And so actually, we for sure know that rock A, since it left the ground at 20, is going to come back at 20. It just happens to be going down. I thought this was a fun question. You know, it's like, what if I change it to the moon's gravity? And if you didn't know, the moon's gravity is really close to 1/6 of Earth. It just works out that the radius of the moon and the mass of the moon, it turns out that it's really, really close to 1/6 of the gravity we experience on Earth. And so it asks what happens to your answers to part A and part B. And so let's just take a look. And if you look back at the algebra, the gravity term actually canceled. So if we mess with gravity, it actually does not mess with the time it takes to hit the collision. However, smaller gravity would allow rock A to go higher, right? It's going to slow it down less. And then rock B, it's not going to pull it down as fast as far. And so actually the collision point is going to be at the same time, but it is actually going to be higher. And so the new collision point, and again, I just graphed the new two things. I just put into these things. This is just G over 6, and this is just G over, G over 6 here and G over 6 here to find the time. But then when you actually want to find the position, again, you're just plugging that in, and you're going to get different positions. So it turns out it intersects more like at 47 feet rather than 18.5. So the intersection is the same time, but it's much higher. Velocities, okay, and the velocities, of course, would change, right? The one is going to be going up much faster, and the other one not going to be going down as much because gravity is pulling you at 1/6 of its normal rate. So I thought that was a fun question. And I think in the sheet maybe it even says a part D, but that was when I had other parts and I kind of redid the question, so you can ignore that. All right, track star, just like Lauren and Helen, but I made it Noah Lyles celebrating his 2024 gold medal in the 100. So we're running 100, that's the total distance. We accelerate for 4 seconds and we finish the race in another 5.8 seconds, right? I give you the total time of 9.8. So obviously you do a little subtraction to get 5.8 for the part 2. And really it boils down to 1, this is a standard velocity acceleration question. And 2, break it up into 2 parts. The total race was 100. Part 1 when he was accelerating, part 2 when he was cruising at constant speed. We know that when he's cruising at constant speed, that's the constant speed he got up to, and then he ran it for a certain amount of time. So x1 represents this, that's when you were accelerating, and this is just the constant velocity you were going times how long you were going it. And then you just throw in numbers, and the only variable you have is acceleration. And again, of course, that constant speed is just that acceleration times time. And the last one, we have relative velocity. This is our helicopter question. This is extremely similar to the last example in the calculus one when we looked at, again, it was a helicopter again, so I didn't change it. I just kept it as the helicopter story. But this must use calculus. You have to use calculus because, look, the position function is cubic. So let's go ahead and take the position function and take a derivative to find velocity. And then I know the book slides out of the door at 3 seconds. So let's go ahead and figure out where I'm located at 3 seconds and how fast I'm moving at 3 seconds. And the idea of relative velocity is that when you're a book and you're in a helicopter and the helicopter is accelerating upwards and moving at a certain velocity, you are actually doing the exact same thing. You two are connected. So when the book slides out of the helicopter, it doesn't immediately fall. It's actually identical to the rocket doesn't fall just because the boosters stop providing thrust. Just like in number one, the rocket goes, it stops thrusting, it enters free fall, but that doesn't mean it actually starts falling. The rocket's going to go up until gravity slows it to zero, then pull it back down. Same thing with the book. When the book slides out of the door of the helicopter, at that moment, it is still going the speed of the helicopter. Now, it no longer will accelerate upward, but it's still going to move upward until gravity slows it down. Again, that's the velocity of the book as if it was launched, because, well, it is going that fast when it slides out. And so I write a new equation down here to represent what's happening to the book the moment it slides out. It's 114 meters in the air, it's going 110 meters up, and it's under the influence of gravity. So gravity is going to slow it down and then speed it up and have it hit the ground. And so the maximum height of the book looks like that 731. It hits the ground at 23 seconds, and how fast it hits the ground looks like 119 meters per second squared. Again, the idea of relative velocity. The book traveling in the helicopter must also be traveling the same speed as the helicopter. When it leaves the helicopter, it will still go up for a little bit until gravity slows it down, then pulls it back to the earth.